And you know that any semiconductor device will depend on temperature. So far we have seen the parameters of JFET. We started with transconductance, drain resistance, amplification. Then we have derived the expression for the voltage and the current. So any doubt in the topic so far, please ask. I'm going to pause for a few seconds. Okay, assuming that the things are very clear, so I'm just moving on to the next topic. So uh, any semiconductor device will have an effect of temperature, correct? So here, then JFET is no exception. So when the temperature is going to change, you will have the change in drain current characteristics as well as the transfer characteristics. So you see here T1, T2, and T3. So as the temperature is as the temperature is increasing, see T3 is the maximum temperature. As the temperature is increasing, the drain current will reduce. And when you plot the drain current for all the three different temperatures, you can see one unique thing. They all will pass through one same point. And that point is called a zero current shift point. Okay, this behavior is observed in the transfer characteristics of the N-channel JFET as a function of temperature. So when you apply three temperatures, T1, T2, T3, where T3 is the largest, T3 is the largest and T1 is the smallest temperature. So when I take three temperatures, T3, T2, T1, and when I plot the drain characteristics, what they find is when the temperature is low, the drain current is high. So as the temperature is increased, the drain current starts reducing from the maximum value. What happens, what makes the drain current to change with temperature? It is going to be dependent on two factors. One is going to be the change, one is going to be mobility. So I told you mobility is the ability of the charge carriers to move when you're going to apply an electric field. But apart from applying electric field, you are also applying change in temperature. So mobility will be impacted. And the depletion region width. The depletion region width is going to be very, very large. Then the charge carriers cannot move freely, right? So in that case, the drain current will be reducing. So these are the two main factors which are contributing to the reduction in drain current because of temperature. One is mobility of majority carriers and the depletion region width. N channel already we are considering electrons as a majority carriers, and electrons are comparatively having a very high value of mobility compared to holes. கரெக்டா ஸோ என் சேனல்லே இந்த ப்ராப்ளம் வருதுன்னா பி சேனல்ல ஆல்ரெடி ஹோல்ஸ் ஆர் மூவிங் வெரி ஸ்லோ. When the temperature is also going to change, it will even make the holes to move very, very slower. So consider how bad the situation is when you are going to use a P channel JFET. So here in N channel JFET, this is the characteristics we are getting. Okay, so mobility of the charge carriers decreases with increase in temperature. It's just like how you get tired during summer. When the heat is high, you get tired. You cannot move fast. Same thing is applicable to your charge carriers also. So when the temperature is going to increase, the carriers cannot move freely. Their movement becomes restricted inside the material. So when the charge carriers cannot move freely, the velocity is reduced. When the velocity is reduced, the drain current is also reduced. Simple. See, all the examples are taken from nature only. So how nature is behaving, the same thing is replicated inside all these devices. Simple example, when you increase the temperature, the current is getting reduced. Means example is yourself. During summer, when you are asked to run for 1 kilometer at 12 o'clock in the noon, you cannot do it very fast as you do in the 6 o'clock in the morning. Because when there is more temperature, energy drain is going to be more. So you will be moving with a reduced velocity, which will impact your capacity, right? Same thing is happening here. So when you increase the temperature, the charge carriers cannot move freely, which will reduce their mobility. When mobility is reducing, the velocity will reduce. When the velocity is reducing, the effective current is going to reduce. That is what the final outcome is, reduced drain current when the temperature is going to increase. So simply, if you want to say one thing, as the temperature is increasing, one nutshell from this you can conclude ID is going to decrease. Very, very important thing. Don't think if you increase the temperature, charge carriers will acquire more energy and they will cross. No, it will not happen in all devices like that. In JFET, a majority carriers are there. It will happen in the reverse way. As the temperature is going to increase, my drain current is reducing because of the reasons listed here. Okay, and you can see the reduction is 0.7 percentage for 1 degree. For every 1 degree rise in temperature, the ID will reduce by 0.7 percentage. And also what happens, or reason is the depletion region width will increase with temperature. The depletion region width decreases with increase in temperature. Okay, so effectively, if you see, this allows ID to increase, and the increase in ID is going to be equivalent to 2.2 millivolt per 1 degree Celsius. See, if the temperature will reduce ID, but when the temperature is increasing, the depletion layer width will start decreasing. So the ID will move even more freely. அதனால our ID ஓட increase வந்து it is 2.2 millivolt per 1 degree Celsius in VGS. Okay, so one thing is disadvantageous to you, but other thing is advantageous to you. So even though ID is reducing, but depletion rate width குறையறதுனால ID will increase, and that is given by this relation. Okay, 2.2 millivolt per 1 degree Celsius. So this phenomenon is same like how we are going to observe the same thing in a bipolar transistor. So if you want to overcome the effects of these temperature compensation in FET, you have to have a biasing circuit called as biasing for zero current drift. Biasing for zero current drift. What is zero current drift? Now, see, when the room temperature, my drain current is 2 milliampere, for example. Room temperature now, what I say is 27 degrees Celsius. At 27 degrees Celsius, the current is 22 milliamperes. And a room temperature 30 degrees Celsius ஆகும்போது my drain current will be reducing to 1.9 milliamperes. So you have seen reduction in drain current, but that reduction should not happen. So that you have to add an additional circuit which will ensure that even at 30 degrees Celsius, my current is still 2 milliamperes. So in the drifting now, changing the value of current. So 2 milliamps to 1.9 milliamps drift has to be avoided. And the current now all other parameters will start reducing. So that circuit is called as zero current drift. Zero current drift na 27 degree kun 2 milliamps, 30 degrees kun 2 milliamps. What is the difference? The difference is zero. Okay, that is called as zero current drift circuit, which will ensure that even when temperature is changing, my current will be constant. That circuit is called as zero current drift biasing circuit. Okay, and they have given all the equation, not that much significant to this derivation. So you can easily derive what is the condition for zero drift. So for zero drift, they say this is the condition for IDS, ID, the modified equation is ID equal to IDSS into 0.63 by VP the whole square, and GM equal to GM naught into 0.63 by VP. Onnolla VGS, they are adding VGS equal to VP plus 0.63. The 0.63 is the compensation done for your zero current drift. Adkan derivation, you see, they have given the derivation, you are getting 0.63 volt as the residual voltage. So in the voltage, the current is getting drifted. So wherever I have VGS, if I am going to add 0.63 volt, then I am going to ensure that the circuit works well for zero drift current. So now conventional JFET equation, I am going to replace VGS by VP plus 0.63. So if I do that, I get the modified equations for the JFET for addressing this issue, zero current drift. Okay, for addressing this issue.